Continuing with our topic on arrays, I wanted to cover one more conceptual issue and then go through a couple more programming practices. We had been talking about arrays in the previous video for this learning module, and we've really been focusing just on what's referred to as single-dimensional or one-dimensional arrays. We would declare our integer array, A1, and we would declare just that single dimension for it, in this case, a single dimension of length 4. That is still a very common use case, but we can have multi-dimensional arrays as well. If we're thinking of the single dimensional array as kind of analogous to a vector as a mathematical term, we can also have equivalent to like a matrix via a two-dimensional array. The syntax is intuitive, but the implications are a little tricky, so I want to cover that. We can declare an integer array called A2 that's of 2 dimensions. In this case, both dimensions are of size 4. And the initialization syntax is a little tricky, but we're basically just doing it row by row. We use actually double curly brackets, and then within that, the first one is going to be the first row, followed by a comma, then the second row, then the third row, followed by the fourth row. This is how we would want to visualize our two-dimensional array, our matrix in memory for that example. We are going to be using two-dimensional matrices, or two-dimensional arrays, in a couple different contexts this semester. Next up is we're going to be using them in the context of having multiple strings in a program. Let's say we want to keep track of a list of names: Joe, Bob, Steve, Clark, Gary. Each of those individual names are themselves one-dimensional arrays. To store the name Joe, we need 3 characters, or potentially a fourth, as we'll cover in the next topic. We need to store that in a single array in and of itself. And then if we want to have multiple names being stored, that would then be the second dimension of our array. So we'll see two-dimensional arrays in that context. I don't think that is necessarily straightforward to work with. We can only get past that by just getting practice and working with two-dimensional arrays. The second context in which we'll see two-dimensional arrays is near the end of the semester, when we'll be looking at image data and doing some high-level image processing. I have a JPEG file, I have a PNG file, and it's this two-dimensional image. And if I want to access each individual pixel inside that image, that's kind of a natural way to lay out data would be via some two-dimensional array or data structure, as we have in the library we're using for image processing. In C, you can actually keep increasing the number of dimensions beyond 2, so you can have 3, you can have 4, you can have 5, you can have 6. It's not that common, to have anything beyond 3 for the kind of data or the nature of data that programmers tend to work with. If you're writing a program and you find yourself putting together a 5-dimensional array, it may be a good time to kind of rethink, and consider the data. Why does it have so many dimensions? 1 is extremely common, of course, as we've seen. 2 is going to be relatively common. 3 is less common, but still certainly exists. 4, 5, 6, 7, something is going on a little atypical in your program, and it may be time to refactor a bit. So in C, we do our subscripting of our arrays going from left to right. I don't really know what else to say about that other than that's just something you have to recognize when looking at multi-dimensional arrays. There's that same data array. We initialize int a of 4, 4. The first dimension can be thought of as the row of our two-dimensional array, and then the second dimension can be thought of as the column of our two-dimensional array. With strings, it's not so bad because you can think of the first dimension is which name, the second dimension is which character inside that name. If Joe was my third name, it would be the third row of this two-dimensional array, and O would be the second letter of that third row here. Image data, it's also okay, although we sometimes get it swapped to row and column, but it's first dimension first, then second dimension. And if you have 5 dimensions, although we really can't visualize that, at least not in PowerPoint, you get dimension by dimension from left to right. So just to walk through very briefly what this means in practice, if we want to then access and print out, we're not actually assigning it. This is more of what is A of 3, 2 of this array. Remember, we're starting with 0, 0, 1, 2, 3, 0, 1, 2. The result would be 15 for A3, 2. There's no really good way in English to say that, but A of 3, 2, or A3, 2, or A sub 3, sub 2, or something is all perfectly valid. 0, 1, 2, 3 for that first dimension, our row of our matrix. 0, 1, 2 for our column, that would be element 15. Pause for a second. What would 1 sub 0 be? It's not this one. We'd be going down one row, 1 column offset 0. 0, 1, 0, 1, 2. The next one would be 7. 0, 1, 2, 3, 0, the next one would be 13, as compared to 0, 1, 2, 3, that would be 4. What would A of 4, 1 be? Well, we're back to that example, what we called array fun from last time. It's outside the valid range of that array. C is not going to throw up a warning. It may or may not have some sort of error. It's not going to be what your program would be expecting to access. Your code is wrong if you're accessing 4, 1. And again, you may be saying, Professor Zambrino, I'll never do that. Obviously, it's of size 4, 4. I've got it memorized. It's 0 to 3 in both dimensions. I'll never put a 4 there and I'll be good to go. In practice, our code isn't necessarily so clean. We're doing things with I++ and I-, and there's multiple dimensions involved. And getting it wrong is just a very common programming mistake. When you're getting crashes, and certainly when your data just doesn't seem right, the same tools and techniques are what you want to follow. I'm not sure if the data is right. Let me print out what I think the data should be. And if it's not what it is, what it's expected to be, I can find the bug. And if it's crashing, it's probably a memory access issue. Let's make sure my array indices are correct. When we start to talk about pointers, you'll see more and more of those kind of crashes, and you'll get adept at being able to track them down and debug them. How this array layout works in practice is actually an implementation detail. If you hear someone refer to C as a row major order in terms of memory layout, that's technically correct. In memory, we're actually laying out the first row, then the second row, then the third row, then the fourth row. So you may find some code bases in which you have a two-dimensional array and it gets kind of flattened as a one-dimensional array. That's a pretty advanced concept. For our examples, if we start with a two-dimensional array, we'll stay with a two-dimensional array throughout. C as a language, as a spec, unlike other higher level languages, does not let you directly copy one array to the next. There is a library function called memcopy that lets you do that. We will play with that later, but without using that functions, just like we saw for the entire array, that you really can't declare it after you've done the initial declaration of it. You can't initialize it after the initial declaration of it. The workaround for that is the exact same. If I want to copy an array to another array, we have to have our loops that are going to keep track of each element of the first array, copy it to the equivalent element in the next array. And this code example here, which I can also bring up, is a very common C programming design pattern. And that is to say, you'll see this kind of code just kind of over and over again in working with two-dimensional data. If I want to copy the whole first array A to the whole second array B, I can't just say B equals A. You'll get a pretty nice warning about that. It's kind of a squiggly line warning in our IDE. The array type is not assignable. I can assign the individual elements of the array. I also can't do just rows of the array. That's valid syntax to request the first and second row of those arrays, but they're just not assignable to each other. We can't access them via an assignment statement. Let's assume there's some initialization of array I, and you may see, like, as I'm typing this, I'm just typing it pretty quickly. I mean, this is such a common design pattern. You have two-dimensional data. You're going to go num rows, num columns with I and j, and it's just going to look so similar. Let's assume we're going to want to initialize I to some random value between the range 0 to 99, right? Mod 100, it's the remainder when divided by 100. Our values will either be 0 up through 99, everything in between with somewhat equal likelihood. We've initialized A. We may want to actually then print our data A. We got a little bit of experience in how we print data a little bit nicer. It's always good practice to remember and learn how to do that. I want to print out this array. Other languages, you just type in the name of the variable in the REPL and you get the result back out. Well, we're not so fortunate with C. Let's say I want to print A's of this size, num rows, num cols. And then I'm really going to use the same exact syntax. Heck, let's copy paste so we don't run into frustrations of getting a typo here along the way. I want to print each row and I want to print each column, basically. So for each row, I want to make sure I have a new line afterwards. For each element inside our column, well, now I want to actually print out the value, maybe with a comma afterwards. And since we're ending a row here, we can end it with an extra curly bracket. Okay, I wrote that code pretty quickly. I wasn't trying to show off. It may come across that way. You're going to get equally adept at that. I have this two-dimensional array. It's of size num rows times num columns. I'm going to have an I loop for the rows, a j loop for the columns, and I'm going to access aij inside that loop. That's just such a common design pattern, just like for the single dimensional example. And that looks kind of meh. What did I forget? Oh, so if I'm going to do that, I also want to add like a starting parenthesis. Technically, how much does it annoy you that there's kind of an ending column? I mean, we can check that, right? If j equals, or how about this instead? We go num columns minus 1, and then because we know that for the very last one, we don't actually want the, all that syntax help is annoying. For the very last one, we don't actually want to print the comma at the end. This is kind of micro optimization, but let's do it. A of I sub what would be the last one? Well, again, there's num columns. So the valid indices for our subscript is 0 to num columns minus 1. I did a minus 1 here to avoid that very last column. If I then now want to print that very last column, I actually use that as my constant offset here. There you go. That's a pretty nicely formatted array. If we want to be really precise, I kind of want to add like an extra parenthesis at the end here. And if this were to be something we actually wanted to copy and paste into our C code, well, okay, good enough. It's got an extra comma, so this would not, we couldn't copy paste this into a piece of C code. I'm not going to stress out about the extra comma. Then we want to actually, copy our loop from one to the other. That code is already in place. B of I sub j is equal to A of I sub j. Let's confirm that it actually works. Well, how do we confirm that copy actually works? There's a couple different ways. I think probably the easiest way to confirm that the copy worked would be to take our really close to correct A printing code and then convert that into B printing code. It shouldn't be a big change. It's the same size arrays. I'm only changing my print calls to either print the value of B instead of the value of A. And while this doesn't look incredible, this code when run, let's try it again here. There we go. I don't know why it kind of blipped on me there. I'd say it looks a little ugly, but they're the same. So the copy actually happened as expected. We went through a doubly nested for loop, and we were able to copy all of array A into array B. We could do further processing as well. I mentioned that there's a system library call that allows us to do block memory copies. I will show it to you, but not expect you to use it as of yet. So this loop is perfectly valid. You want to copy one multi-dimensional array of any number of dimensions to another multi-dimensional array, that will work. But there's a function that does exist in the standard C library, so you can always expect it. It's called memcopy. Copy into a pointer of B, and the name of an array is a pointer to the first element from a location pointed to by B, a certain number of bytes. So that's a little ugly. We have to think about how many bytes is A and how many bytes is B. We're going to be using some of these functions later on, so being able to calculate the number of bytes we want to work with is important for a lot of these functions. For allocating memory, and in this case for copying memory, we need to be able to figure out programmatically how many bytes are in A and are in B. Can we figure it out just by looking at the declaration? How many bytes are in A? We know how many integers there are. There's this many, 5 rows, 10 columns. There's 50 integers. Of course, the reason we have those pound defined is that we don't have to or don't want to hard code it elsewhere in our code. There's that many integers. But the function doesn't ask for the number of integers to copy. It turns out it asks for the number of bytes. Each of those integers is of size byte, right? Each byte is, depending on the system, but generally 4 bytes wide. 5 times 10 times 4, 200 bytes are going to get copied. It's complaining about something because technically this is defined in string.h. I think it'll compile anyway, even if it can't find it at compile time. And it did. We were able to copy that function from one to the other without too much trouble there. Either approach is fine. Once you become adept with doing memcopy, I think it's safe to assume the authors of memcopy will write faster code than you did, but this code's a little harder to read as well, right? I mean, it's a somewhat obtuse kind of syntax. The destination goes first, then the source, and then you do have to calculate the correct number of bytes to do the copy. Either approach is totally fine for doing an array copy, and that's just showing that while we can't access the individual arrays as kind of first-class elements of the language like some other languages allow, there is no print array kind of built into the language or copy array built into the language. via just some clever, formatting prints that we write ourselves and some system calls that allow us to kind of just manage blocks of data at a time, we get something a lot closer to what we would hope to have here. Let's attempt to put it all together and look back to learning module 3 where we were sorting all of 5 numbers, right? Where we don't need to see the whole visualization. We were using bubble sort and we were attempting to sort 5 values. I have the code here. I can bring it back up. This was sort vals back from LM-03. It doesn't really matter. We were playing around with like numbers that went backwards to confirm that it actually worked. 8, 9, 10, 11, 12, 12, 11, 10, 9, 8. So the question really is, can we write a loop that does this operation for us? And I would say a secondary but equally important question is, can we use arrays also to make it a much more powerful version of the same? A lot of this code can and should be copy-paste. So I actually want us to start with a copy-paste. You always have to be a little bit careful when you copy-paste things that you're actually getting the correct value. So let me make sure I'm opening up the right code here. We want to do our sort array or our array sort function. I'll open it up in just a second. This is under learning module 5 and it's .4. It's called array sort. And as we get started with it here, we're going to want to just copy paste what we already have. Let me get that a little bit more set for us here. 1 second. Okay, I think I have it copy pasted. It should compile. I think when we copy paste, we always have to be a little bit careful that what we're doing is actually going to still compile and run. This is just the exact same code now just copied into a different repository, which is fine. So it's here, it's still sorting. Input is 5 integer values in any order. The output is a printout of the 5 input values. First, allow me to suggest that I'm getting really sick of printing out or typing in values each time. Let me just refactor the code a little bit to do this random number seeding like we've been doing in a lot of our programming practices. This is here so that we don't have to type in a lot of data to test a program. Enter n. Sometimes the prompt is enter in a random number seed, but it's requesting the same thing. Let's grab n here and use it to seed a random number generator. You've seen this block of code, at least I believe you have, in a lot of different examples. And it's not there because, I want you to have to worry about random inputs. It just makes testing a lot easier. By just changing the random seed, we can get different inputs without having to type and type and type and type. And now for our var1 through var5, now I can just do some random generation. So let's say var1 equals rand. How about we get something in the range 0 to 50. Oh, I should be copying, pasting, and not having to retype over and over again. And there's 5 of them. And I believe, we did have some printf prompts that are, we did have it before sorting. I think I might have deleted it just now. Let's add this back in here. Before sorting, because you don't know if it's working if you're not printing it beforehand. N doesn't really matter. So there is no good N, no bad N. The seeds are kind of arbitrary. Sometimes when I'm setting the seeds for your tests, I'm doing so because I've tested it myself and I knew that this random seed led to an interesting edge case or not. Boy, this data looks awfully sorted to begin with. 7, 13, 14. It's almost entirely sorted, but it was not entirely sorted. Let's find a different one that has maybe a slightly different sort scenario. Okay, this one seems better. Seed 11 we'll use to start with. 17, 47, 42, 5, 21. The end result is it is now sorted, and our code still works. That's all I've tested so far. We've changed it to kind of random number generation versus manual enter of all that data. And we're doing this same operation over and over again, right? We were checking all the values with their neighbor values, and when we realized that kind of partially sorted it, we just kind of kept repeating it. Well, that sounds like something that could be automated in a for loop. We didn't actually define a length, but let's do so. Again, wherever the compiler now sees the word length, literally if I called a variable var1 length, it would also replace that with var15. But wherever it sees the word length, those characters in the code, it does a pre-processing pass and replaces it with 5. Syntactically, what I don't love here, although I told you it wasn't strictly necessary, is you're indenting level to make it more obvious that this is within the loop that's containing it. I believe, although editors handle this differently, I'm pretty sure we can just do that. Yeah, we can tab the whole selection. I don't know if we can untab the whole selection. Oh, I hope this works. I'm pretty sure we should get the same exact result. And we do. It still works. What did we do here? We used our for loop to automate for us, right? Where I said, yes, you can keep copy pasting code. Would it work for 5 million entries or not? At least for 5 entries, we have our for loop. It's doing the same exact code 5 times. It's technically now a little bit redundant, right? Because we didn't actually need to compare var4 versus var5 the second, third, fourth, and fifth times through that loop. But there's also no harm. They're already sorted. Comparing them is just extra work. It's not going to make the result wrong for us. That works. We have our array of size 5. We now should be able to make, we have our length. We have our variables. There are 5 different ones. We should be able to make an array version of this. Now we're declaring an array of length 5. Those variables are going to be invalid, so we're going to have to be careful as we write this code here that we didn't mess it up. var1, var2, var3, var4, var5. I would argue the code's going to get a little bit simpler, not harder. We know there's length things. We know there's 5. And we know it's not var1 through 5. It's array, not 1 through 5, but 0 through 4, right? Array of I equals rand mod 51. I know I can sometimes be annoying with the programming practices where I say, generate a random number in the range 13 to 74. I want you to just explore and understand how the mod operator works, and you'll become pretty adept at it at that point. Okay, so we've initialized, and because of how we're doing the seeding, it in fact should still be the same 5 numbers. Our print loop will not work yet either, but we can kind of print it out like we did before, where we're saying A of size length. And then we have another loop in then here. And we're doing this so much, let me just copy paste this here, right? For I equals 0, I is length less than length. Now we're going to want to print out just the next value. This will have a superfluous comma, and if the specification of your program does not allow for the superfluous comma, you saw in the previous example how we resolved that. You just have to have an edge case for length minus 1. We're going to leave the superfluous comma in there. Since this code block should be okay, let's then add it back here as well, except it'll say after sorting. And I called it A here, but we actually declared and called the variable array. So let's make sure we're consistent with that. The rest of this code, this is a pretty big refactor, is no longer using var1, var2, var3, var4. Let's just do a search and replace. I don't know if this editor is good enough. Oh, it's all right. Search and replace. Instead of var1, we want to instead do array of 0. Instead of var2, we want array of 1. Instead of var3, we want array of 2. We're getting there. Instead of var4, we want array of 3. You're kind of seeing how, like, when we named it starting with 1, everything is off by 1. That's how our array indices work. So that's not surprising to me, at least, that everything is kind of off by 1. We have still kind of hard-coded in a sense here, but those 0 to 1, 1 to 2, 2 to 3, 3 to 4, we have completely refactored the code to now use arrays. Shockingly, it worked on the first time. I would say this is still not quite as good as we can do with arrays, because for length 5, this code works. As soon as I change this to length 6, this code no longer works. It's hard-coded that it's only looking at 5 elements. Well, we may be able to see structure that it's 0 to 1, it's 1 to 2, etc., etc. Well, there's a general case here, right? Is array of I greater than array of I plus 1? We should swap them. Let me just write that. Let me just copy paste this as an example, and then we'll see what this would mean in practice. Is array of, and let me, just to make things clear, it's not a I. I is the number of times we're doing it. Let's make a separate index j. Is array j greater than array j plus 1? We haven't defined j yet. I know you look at this and you do see syntax error, which is correct. We'll fix it. Array j, is it greater than array j plus 1? That's true for j equals 0. That's true for j equals 1. That's true for j equals 2. And for j equals 3. We need to have a loop that then iterates from j equals 0 to j equals 3. And it's not entirely just 3, but then it would be length minus 1, right? We could have hard-coded 3 and then it would work for this one circumstance. I think I need that closing the closing brace there. And then that's replicating or getting rid of all that code that we have there. Let's take another look for sanity checking here. Is array j greater than array j plus 1? We don't want to go length here. That would do array index of 4 is it greater than array index of 5, and array index of 5 is not valid for this, right? So length minus 1, we're not actually checking the last element to anything else. We're stopping before we get to that last element. We have a sorted array still. Now we have a little bit of power in our program. Instead of 5, let's make it 50. This is why our arrays and our for loops are so powerful. We went from a size 5 sort to a size 50 sort. We changed nothing, right? The problem is we're generating random numbers in the range 50. So as we increase the size of our array, there's going to be a lot of copies. Because there's only so many numbers you can generate in that range. Well, of course, in this case, now printing is taking longer than everything else. And there we are. It looks like there's a lot of repetition because there are, right? There's 50,000 numbers, and they only have 50 possible values, so there's going to be like 1,000 copies of each number. The sort was a little slow there. We can actually make it just a little bit faster by recognizing, right? In our original code as we had done it, let me see if I can go back if I still have the example open here. In our original code as we had done it, what did we do, right? We instead, I don't have it open. Oh, it's on this tab right here. We instead did all 5 numbers, then just 4 numbers, then 3 numbers, then 2 numbers, then 1 numbers. We can actually do the same thing right here with our bubble sort implementation. We can say, first time through, do all I numbers. And then as I increases from 0 to 1, do 1 fewer number, then 2 fewer numbers, then 3 fewer numbers. It's hard to say because the printing itself took so long for the actual output here. But in doing that, it should make the code significantly faster. I don't know if we'll be able to measure, tell that on a measurable level. Yeah, it was significantly faster than it was before we did all length times length iterations. Now it's roughly length times length over 2 iterations. This implementation, and I would say this implementation with the I minus 1 part added to it, this is very, I call it, textbook bubble sort. Something that some of your contemporaries won't learn to do until they're juniors. You have it here. This kind of gets the job done for array sort implementations. I want us to leave things here for now. Hopefully you felt that was a useful exercise to go through in terms of understanding arrays, both multidimensional and doing more complicated operations with single-dimensional arrays. Your programming practices are very similar to these examples that we went through today and in the previous video. There's one that involves counting like string frequency and duplicates, but your strings are just arrays of characters. And when you kind of connect those dots together, it is a very solvable problem as well. Good luck, and of course, let me know as always if you have any questions.